Welcome to the finale of our tale of three intersecting lines. Last time, we proved the 180-degree angle sum rule. Today, we face a new mechanical problem, measuring the exact height of a shape using tools built for structural accuracy. In geometry, that height is called an altitude. It is a line segment that drops straight down from a vertex until it hits the opposite baseline at an exact 90-degree angle. Where these altitudes land depends on the triangle's angles. Inside an acute triangle, all three possible paths drop safely within the shape's boundaries. In a right-angled triangle, the geometry is even more efficient. The two sides that form the 90-degree corner already act as built-in altitudes. Obtuse triangles are the exception. To drop a perpendicular line from an overhanging vertex, you have to extend the baseline outward, meaning the altitude falls outside the triangle itself. Mastering these altitudes is the first step in identifying the absolute shortest path between a specific point and a flat line. It is nearly impossible to find that 90-degree drop by sight alone. Estimating the angle freehand leads to slanted, inaccurate lines that throw off the entire measurement. To get a precise result, draftsmen use a straight-edge ruler paired with a transparent set square. The technique involves 3 steps. First, align the ruler along the baseline. Second, place the set square flat against the ruler. Finally, slide the set square until its vertical edge touches the top vertex. This mechanical process ensures the line is exactly 90 degrees, removing the uncertainty of freehand sketching. Once we can measure these sides and angles, we can organize every triangle into specific categories using 2 distinct lenses. First, classifying by side length. Equilateral triangles have 3 matching sides. Isosceles have 2 matching sides. Scalene triangles have none. Second, by interior angles. Acute triangles have angles under 90 degrees. Right triangles have one 90-degree corner. Obtuse triangles have one angle over 90. These systems can absolutely overlap. An isosceles right triangle, for instance, features a 90-degree corner alongside 2 matching 45-degree angles. However, some combinations are impossible. An equilateral triangle can never be right-angled because its 3 equal sides force all angles to be exactly 60 degrees. These classifications provide the foundational vocabulary for identifying and defining any triangle you encounter. Intriguing. We can apply this same 2D logic to solve a spatial problem in 3 dimensions, the spider box riddle. A flightless spider sits at the bottom corner of a closed box. Its goal is a bug at the farthest opposite top corner. To reach it, the spider must crawl across the surfaces of the box. Most people assume the quickest route is to crawl along the bottom edge to the far corner, then climb straight up the side wall. Geometry offers a different perspective. If you unfold the 3D box into a 2D cardboard net, the relationship between the start and end points becomes visible on a single flat surface. On this flat plane, the absolute shortest path between the spider and the bug is a single straight line. When you fold the box back together, that line reveals the true shortcut, cutting diagonally across 2 adjacent faces of the box. Flattening a 3D surface into a 2D plane simplifies the problem. It shows that finding the shortest path in 3 dimensions often begins by looking at the surfaces in 2. You have covered the fundamentals of intersecting lines, from constructing SSS and SAS triangles to tracing altitudes and unfolding spatial puzzles. Here's a final challenge. Construct a right-angled triangle where angle B is exactly 90 degrees and its hypotenuse AC is exactly 5 centimeters. Consider how many valid triangles you can create with those specific measurements. To find the answer, try treating side AC as the diameter of a circle and drawing a semicircle above it. Work through the logic and share your findings in the comments.